So this is the quantum bound state PhET simulation. So to go through a little bit the worksheet, the first question is, what is the highest probability of finding the energy eigenstates? So if you notice, our lowest state's just kind of down near the bottom, but as we go to higher and higher energies, we see this sort of shape that our amplitude, for lack of a better term, is highest at the edges. And so our highest probability is actually near the edges of the well. You have a lower probability near the center. And the semi-classical explanation we use for this is that our particle, if we imagined a classical particle, is moving faster in this area, so it spends less time there. And so that is kind of one way to think about that, but remember that this is analogous. So the question of whether the energy eigenstates really correspond to a mass going back and forth on a spring, well, not really, because in this case, it isn't necessarily that the particle starts here, goes back and forth, right? This is our probability distribution. If I switch to the wave function, we see that we really have to think about our energy eigenstate as being spread out over this whole well. It is not the case that in time it starts one corner and then rolls up to the other. That's just not what's happening. We're now going to look at a superposition, and so I've entered the numbers already, and you can notice, if you imagine making a histogram of these coefficients in your head, that this is somewhat Gaussian, that the values in the middle have the highest probabilities. So let's see what this looks like. So I've paused the simulation. We see that it's starting off to the side, and let's look first at the wave function. And so we see the wave function is oscillating and it seems to be moving from one side of the well to the other. So let's go back to the beginning, switch to probability density, speed it up a little bit, and now watch it. So we see that in fact our particle is going back and forth. So it has kind of this spiky appearance when it gets near the edge, but in the middle we see that it's kind of a nice spread out Gaussian. Now, one thing to keep in mind is notice that the same thing is repeating over and over and over again. When we looked at similar superposition states in the square well rather than the harmonic oscillator, we kind of saw it spread out but then just get really messy with time. So we see this repeating pattern. We do not call this a coherent state because we do see the shape of our wave packet. We've made something that looks like a wave packet. We do see it changing with time, though its behavior is still periodic. So this would not be considered a coherent state, it's simply a periodic state. Let's briefly look at some other superposition states. So I could pick two higher energy states and set basically an equal probability. And that now when we watch, we see that it does look like it's going back and forth, but kind of less so. We don't see as much of a wave packet as much as mostly on the left to mostly on the right. Again, you do see kind of that nice repeating behavior. If we look at the wave packet, it's less clear what's happening. We gotta slow that sucker down a little bit. And now you can kind of see a little more what's happening with time. Now I've created a different superposition state where these are quite spread in energy, but again, in this case, I've used equal probability, equal magnitudes. If I look at the probability density function, we see something that looks kind of disgusting, and it does still look like something is, I guess, going back and forth, but it's not very pretty. We can ask what happens if I make it an unequal superposition state. So I'll normalize this after I enter the values. So normalize it so it's mostly, I don't love the lack of sig fig, so it's mostly this lower energy state and only a little bit this higher energy state. And now when we watch, we just see some slight shifts. So it doesn't seem like a lot is happening now because it's almost entirely that lower state. So maybe we have to make this a little bit more obvious. Okay, what about, oops, that's not what I meant to do. So if it's 0. Watching someone else use a computer is so frustrating, I'm sure. Oh, it still really wants to not normalize well for me. Okay, 0.1. What about now? Will you like that? Okay, good enough. So yeah, you just see kind of small little shifts. And again, when we look at the wave function, we can kind of see a little bit of messiness here. But again, there's this periodic behavior happening. So for any superposition that we are creating in this harmonic oscillator, there's very quickly a repeating behavior. However, this is very much not a coherent state since we don't see for instance, a wave packet traveling clearly together.